Any quick questions about Torch? Yeah.
When you mentioned that it's efficient to run for loops, so are you saying, for example, in our convolutional net layer, we used to have 4 layers in the naive version, and in the fast one, you just call. So do you still gain any benefit to?
Yeah, you definitely still gain benefit from writing more efficient code, but it's not. Oh, so the question was about how bad are for loops in Lua. And Python is interpreted, right? So that's really why for loops are really bad in Python, because it's interpreted, and every for loop is actually doing quite a lot of memory allocation and other things behind the scenes. But if you've ever used JavaScript, then loops in JavaScript tend to be pretty fast, because the runtime actually compiles the code on the fly down to native code. So loops in JavaScript are really fast. And Lua actually has a similar mechanism where it'll sort of automatically and magically compile the code for you into native code, so your loops can be really fast. But definitely writing custom vectorized code still can give you a lot of speed up. All right, so we've got now maybe half an hour left to cover 2 more frameworks, so we're running out of time. So next up is Theano. So Theano is from Yoshua Bengio's group at University of Montreal, and it's really all about computational graphs. So we saw a little bit in NNGraph from Torch that computational graphs are this pretty nice way to stitch together big, complicated architectures. And Theano really takes this idea of computational graphs and runs with it to the extreme. And it also has some high-level libraries, Keras and Lasagna, that we'll touch on as well. So here's this same computational graph we saw in the context of NNGraph before. And we can actually walk through an implementation of this in Theano. So you can see that in here, we're importing Theano and the Theano tensor object. And now here, we're defining x, y, and z as symbolic variables. This is actually very similar to the NNGraph example we saw just a few slides ago. So that these are actually not NumPy arrays. These are sort of symbolic objects in the computation graph. Then we can actually compute these outputs symbolically. So x, y, and z are these symbolic things, and we can compute a, b, and c just using these overloaded operators. And that'll be building up this computational graph in the back end. Then once we've built up our computational graph, we actually will want to be able to run certain parts of it on real data. So we call this Theano.function thing. So this is saying that we want to take, our function will take inputs x, y, and z, and it'll produce outputs c. And this will return an actual Python function that we can evaluate on real data. And I'd like to point out that this is really where all the magic in Theano is happening. That when you call to function, it can be doing crazy, crazy things. It can simplify your computational graph to make it more efficient. It can actually symbolically derive gradients and other things. And it can actually generate native code. So when you call function, it actually sometimes compiles code on the fly to run officially on the GPU. So all the magic in Theano is really coming from this little innocent-looking statement in Python. But there's a lot going on under the hood here. And now once we've gotten this magic function through all this crazy stuff, then we can just run it on actual NumPy arrays. So here we're instantiating XX, YY, and ZZ as actual NumPy arrays. And then we can just evaluate our function and pass in these actual NumPy arrays to get the values out. And this is doing the same thing as doing these computations explicitly in Python, except that the Theano version could be much more efficient due to all the magic under the hood. And the Theano version actually could be running on the GPU if you have that configured. But unfortunately, we don't really care about computing things like this. We want to do neural nets. So here's an example of a simple 2-layer ReLU net in Theano. So the idea is the same, that we're going to declare our inputs. But now instead of just x, y, and z, we have our inputs in x, our labels in y, which are a vector, and our 2 weight matrices, w1 and w2. So we're just sort of setting up these symbolic variables that will be elements in our computational graph. Now for our forward pass, it looks kind of like NumPy, but it's not. These are operations on these symbolic objects that are building up the graph in the back end. So here we're computing activations with this dot method that is matrix multiply between these symbolic objects. We're doing a ReLU using this library function, and we're doing another matrix multiply. And then we can actually compute the loss, the probabilities and the loss using a couple other library functions. And again, these are all operations on these symbolic objects that are building up the computational graph. So then we can just compile this function. So our function is going to take our data, our labels, and our two weight matrices as inputs. And as outputs, that'll return the loss in a scalar and our classification scores in a vector. And now we can run this thing on real data, just like we saw on the previous slide, where we can instantiate some actual NumPy arrays and then pass them into the function. So this is great, but this is only the forward pass. We actually need to be able to train this network and compute gradients. So here, we just need to add a couple lines of code to do that. So this is the same as before. We're defining our symbolic variables for our inputs and our weights and so forth. And we're running the same forward pass as before to compute the loss, symbolically. Now the difference is that we actually can do symbolic differentiation here. So this dw1 and dw2, we're telling Theano that we want those to be the gradient of the loss with respect to those other symbolic variables w1 and w2. So this is really cool. Theano just lets you take arbitrary gradients of any part of the graph with respect to any other part of the graph, and now introduce those as new symbolic variables in the graph. So that you can really go crazy with that. But here in this case, we're just going to return those gradients as outputs. So now we're going to compile a new function that, again, is going to take our inputs, our input pixels x and our labels y, along with the two weight matrices. And now it's going to return our loss, the classification scores, and then also these two gradients. So now we can actually use this setup to train a very simple neural network. So we can actually just use gradient descent, implement gradient descent in just a couple lines using this computational graph. So here we're instantiating actual NumPy arrays for the data set and the vectors, and some random weight matrices as, again, actual NumPy arrays. And now every time we make this call to f, then we get back NumPy arrays containing the loss and the scores and the gradients. So now that we have the gradients, we can just make a simple gradient update on our weights and then run this in a loop to train our network. But there's actually a big problem with this, especially if you're running on a GPU. Can anyone spot it? Totally lost? So the problem is that this is actually incurring a lot of communication overhead between the CPU and the GPU. Because every time we call this f function and we get back these gradients, that's copying the gradients from the GPU back to the CPU. And that can be an expensive operation. And now we're actually making our gradient step. This is CPU computation in NumPy. So it would be really nice if we can make those gradient updates to our parameters actually directly on the GPU. And the way that we do that in Theano is this with this cool thing called a shared variable. So a shared variable is a part of the network that actually is a value that lives inside the computational graph and actually persists from call to call. So here, this is actually quite similar to before, that now we're defining our same symbolic variables x and y for the data and the labels. And now we're defining a couple of these new funky shared variables for our two weight matrices. And we're initializing these weight matrices with NumPy arrays. And now this is the exact same code as before. We're computing the forward pass using these library functions all symbolically. Then we're computing the gradients. But now the difference is in how we define our function. So now this compiled function does not receive the weights as inputs, because those actually live inside the computational graph. Instead, we just receive the data and the data and the labels. And now we are going to output the loss rather than outputting the gradients explicitly. And instead, we actually provide these update rules that should be run every time the function is called. So these update rules, notice, are little functions that operate on these symbolic variables. So this is just saying that we should make these gradient descent steps to update W1 and W2 every time we run this computational graph. So we include this update. And now, to train this network, all we need to do is call this function repeatedly. And every time we call the function, we will make a gradient step on the weights. So we can just train this network by just calling this thing repeatedly. And in practice, when you're doing this kind of thing in Theano, you'll often define a training function that you'll call that'll update the weights, and then also an evaluate function that'll just output the scores and not make any updates. So you can actually have multiple of these compiled functions that evaluate different parts of the same graph. Yeah?
So I'm curious if you know how it computes the gradient. Is it like a numerical approximation, or does it parse out the AST of their command and differentiate it?
Yeah, so the question is how we compute gradients. And it actually does it symbolically, sort of parsing out the AST. Well, it's not actually parsing out the AST, because every time you make these calls, it's sort of building up this computational graph object. And then you can compute gradients by just adding nodes onto the computational graph object.
But
so
you would have to know the operators and what their derivatives are.
Yeah. So it needs to know for every of these basic operators, it knows what the derivative is, and it's still the normal type of backpropagation that you'll see in other frameworks. The pitch with Theano is that it works on these very, very low-level basic operations, like these element-wise things and matrix multiplies, and then it is hoping that it can compile efficient code that combine those and simplify it symbolically. And that, I'm not sure how well it works, but that's at least what they claim to do. So there's a lot of other advanced things that you can do in Theano that we just don't have time to talk about. So you can actually include conditionals directly inside your computational graph using these if-else and switch commands. You can actually include loops inside your computational graph using this funny scan function that I don't really understand. But theoretically, it lets you implement recurrent networks quite easily. Because you can imagine to implement a recurrent network in one of these computational graphs, all you're doing is passing the same weight matrix into multiple nodes. And scan actually lets you sort of do that in a loop and have the loop be part of an explicit part of the graph. And we can actually go crazy with derivatives. We can compute derivatives of any part of the graph with respect to any other part. We can also compute Jacobians by computing derivatives of derivatives. We can use L and R operators to efficiently do matrix vector multiplies of vectors and Jacobians. So you can do a lot of pretty cool derivative type stuff in Theano that's maybe tough in other frameworks. And it also has some support for sparse matrices. It tries to optimize your code on the fly and do some other cool things. Theano does have multi-GPU support. There's this package that I have not used, but that claims that you can get data parallelism, so distribute a mini batch, split it up over multiple GPUs. And there's experimental support for model parallelism, where this computational graph will be divided among the different devices. But the documentation says it's experimental, so it's probably really experimental. So you saw when working with Theano that the API is a little bit low level, and we need to sort of implement the update rules and everything ourselves. So Lasagna is this high-level wrapper around Theano that sort of abstracts away some of those details for you. So again, we're sort of defining symbolic matrices, and Lasagna now has these layer functions that will automatically set up the shared variables and that sort of thing. We can compute the probability and the loss using these convenient things from the Lasagna library. And Lasagna can actually write these update rules for us to implement atom and Nesterov momentum and other fancy things. And now when we compile our function, we just pass in these update rules that were already written for us by Lasagna. And all of the weight objects were taken care of for us by Lasagna as well. And then at the end of the day, we just end up with one of these compiled Theano functions, and we use it the same way as before. There's another wrapper for Theano that's pretty popular called Keras, which is even more high level. So here we're making a sequential container, and we're adding a stack of layers to it. So this is kind of like Torch. And now we're making this SGD object that is going to actually do the updates for us. And now we can train our network by just using the model.fit method. So this is super high level, and you can't even tell that you're using Theano. And in fact, Keras will actually use TensorFlow as a backend as well, so you don't have to use Theano with it. But there's actually one big problem with this piece of code. And I don't know if you're experienced with Theano, but this code actually crashes. And it crashes in a really bad way. This is the error message. So we get this giant stack trace, none of which is through any of the code that we wrote. And we get this giant value error that doesn't make any sense to me. So I'm not really an expert in Theano, so this was really confusing to me. So we wrote this kind of simple-looking code in Keras, but because it's using Theano as a backend, it crapped out and gave us this really confusing error message. So that's, I think, one of the common pain points and failure cases with anything that uses Theano as a backend, that debugging can be kind of hard. So like any good developer, I Googled the error, and I found out that I was encoding the y variable wrong, and I was supposed to use this other function to convert my y variable, and that made the problem go away. But that was not obvious from the error message. So that's something to be worried about when you're using Theano. Theano actually has pre-trained models. So we talked about Lasagna. Lasagna actually has a pretty good model zoo of a lot of different popular model architectures that you might want. So in Lasagna, you can use AlexNet and GoogleNet and BGG. I don't think they have ResNet yet, but they have quite a lot of useful things there. And there are a couple other packages I found that don't really seem as good, except, I mean, this one's clearly awesome because it was a CS231N project from last year. But if you're going to pick one, I think probably the Lasagna model zoo is really good. So from my one-day experience of playing with Theano, the pros and cons that I could see were that it's Python and NumPy, so that's great. This computational graph seems like a really powerful idea, especially around computing gradients symbolically and all these cool optimizations. Especially with RNNs, I think could be much easier to implement using this computational graph. Raw Theano is kind of ugly and gross, but especially Lasagna looks pretty good to me and sort of takes away some of the pain. The error messages can be pretty painful, as we saw. And big models, from what I've heard, can have really long compile times. So that when we're compiling that function on the fly, for all these simple examples, that pretty much runs instantaneously. But when you're doing big, complicated things like neural Turing machines, I've heard stories that could actually take maybe half an hour to compile. So that's not good, and that's not good for iterating quickly on your models. And another sort of pain point is that the API is much fatter than Torch, that it's doing all this complicated stuff in the background, so it's kind of hard to understand and debug what's actually happening to your code. And then pre-trained models are maybe not quite as good as Caffe or Torch, but it looks like Lasagna is pretty good. OK, so we've got 15 minutes now to talk about TensorFlow. Although first, if there's any questions about Theano, I can try. OK, guess not. So TensorFlow. TensorFlow is from Google. It's really cool and shiny and new, and everyone's excited about it. And it's actually very similar to Theano in a lot of ways, that they're really taking this idea of a computational graph and sort of building on that for everything. So TensorFlow and Theano are actually very, very closely linked in my mind. And that's sort of why Keras can get away with using either one as a backend. And also kind of one maybe point to make about TensorFlow is that it's sort of the first one of these frameworks that was designed from the ground up by professional engineers. So a lot of these other frameworks sort of spun out of academic research labs, and they're really great, and they let you do things really well, but they were sort of maintained by grad students. Especially, so Torch especially is maintained by some engineers at Twitter and Facebook now, but it was originally an academic project. And for all of these, I think TensorFlow was the first one that was from the ground up from an industrial place. So maybe theoretically that could lead to better code quality or test coverage or something. I don't know. I'm not sure.
So quick comment about that. TensorFlow's code is super, super dense, whereas Theano's code is pretty readable. So there's the downside. Like if you dig into TensorFlow internals, it's a lot scarier than the Theano internals, which are like a grad student code. You can kind of get what's going on. That's a trade-off there.
Yeah, so I didn't try to look into the code base. I thought they both seemed pretty scary. So here's our favorite two-layer ReLU net. We did it in all the other frameworks. Let's do it in TensorFlow. So this is actually really similar to Theano. So you can see that we're importing TensorFlow. And in Theano, remember, we had these matrix and vector symbolic variables. In TensorFlow, they're called placeholders, but it's the same idea. These are just creating input nodes in our computational graph. We're also going to define weight matrices. In Theano, we had these shared things that lived inside the computational graph. Same idea in TensorFlow, except they're called variables. We just like in Theano, we computed our forward pass using these library methods that operate symbolically on these things and build up a computational graph. So that lets us easily compute the probabilities and the loss and everything like that symbolically. This part actually, I think, to me, looks more like Keras, or rather, it looks a little bit more like Keras or Lasagna than raw Theano. But we're using this gradient descent optimizer, and we're telling it to minimize the loss. So here, we're not explicitly spitting out gradients, and we're not explicitly writing update rules. We're instead using this pre-built thing that just sort of adds whatever it needs to into the graph in order to minimize that loss. And now, just like in Theano, we can actually instantiate using actual NumPy arrays some small data set, and then we can run in a loop. So in TensorFlow, when you actually want to run your code, you need to wrap it in this session code. I don't really understand what it's doing, but you got to do it. Although actually what it's doing is that all this stuff is sort of setting up your computational graph, and then the session is actually doing whatever optimization it needs to actually allow you to run it. Yeah?
What's one hot? In the previous slide, you said y is one hot.
Oh yeah. So the question is, what is one hot? So if you remember in your assignments, when you did like a softmax loss function, the y was always an integer, telling you which thing you wanted. But in some of these frameworks, instead of an integer, it should be a vector where everything is 0 except for the one that was the correct class. So that was actually the bug that tripped me up on Keras back there, was the difference between one hot and not one hot. And it turns out TensorFlow wants one hot. Whatever. Right? So then when we actually want to train this network, then we call so in Theano, remember, we actually compiled this function object and then called the function over and over again. The equivalent in TensorFlow is that we call the run method on the session object, and we tell it which outputs we want it to compute. So here we're telling it that we want to compute the train step output and the loss output, and we're going to feed it these NumPy arrays into these inputs. So this is kind of the same idea as Theano, except we're just calling the run method rather than explicitly compiling a function. And in the process of evaluating this train step object, it'll actually make a gradient descent on the weights. So then we just run this thing in a loop, and the loss goes down, and everything is beautiful. So one of the really cool things about TensorFlow is this thing called TensorBoard that lets you easily visualize what's going on in your network. So here is pretty much the same code that we had before, except we've added these 3 little lines. Hopefully you can see it. If not, you'll have to trust me. So here we're computing a scalar summary of the loss, and that's giving us a new symbolic variable called loss summary. And we're computing a histogram summary of the weight matrices W1 and W2. And those are giving us new symbolic variables W1 hist and W2 hist. Now we're getting another symbolic variable called merged that kind of merges all those summaries together using some magic I don't understand. And we're getting this summary writer object that we can use to actually dump out those summaries to disk. And now in our loop, when we're actually running the network, then we tell it to evaluate the training step and the loss like before, and also this merged summary object. So in the process of evaluating this merged summary object, it'll compute histograms of the weights and dump those summaries to disk. And then we tell our writer to actually add the summary. So I guess that's where the writing to disk happens. So once you run this thing, then you get while this thing is running, it's sort of constantly streaming all this information about what's going on in your network to disk. And then you just start up this web server that ships with TensorFlow called TensorBoard, and we get these beautiful, beautiful visualizations about what's going on in your network. So here on the left, remember we were getting a scalar summary of the loss. So this actually shows that loss was going down. I mean, it was a big network and a small data set, but that means everything is working. And this over here on the right-hand side is showing you histograms over time, showing you the distributions of the values in your weight matrices. So this stuff is really, really cool. And I think this is a really, really beautiful debugging tool. So when I've been working on projects in Torch, I've written this kind of stuff myself by hand, where I'm just kind of dumping JSON blobs out of Torch and then writing my own custom visualizers to view these kind of statistics, because they're really useful. And with TensorFlow, you don't have to write any of that yourself. You just add a couple lines of code to your training script, run their thing, and you can get all these beautiful visualizations to help your debugging. TensorFlow or TensorBoard can also help you even visualize what your network structure looks like. So here we've annotated our variables with these names. And now when we're doing the forward pass, we can actually scope some of the computations under a namespace. And that sort of just lets us group together computations that should belong together semantically. Other than that, it's the same thing that we saw before. And now if we run this network and load up TensorBoard, we can actually get this beautiful visualization for what our network actually looks like. And we can actually click in and look and see what the gradients and the scores and really help debug what's going on inside this network. And you see these loss and scores. These are the semantic namespaces that we defined during the forward pass. And if we click on the scores, for example, it opens up and lets us see all of the sub-operations that appear inside the computational graph for that node. So I thought this was really cool, right? It lets you like really easily debug what's going on inside your networks while it's running. And you don't have to write any of that visualization code yourself. So TensorFlow does have support for multi-GPU. So it has data parallelism, like you might expect. So I'd like to point out that actually this distribution part is probably one of the other major selling points of TensorFlow. That it can try to actually distribute the computational graph in different ways across different devices, and actually distribute that graph smartly to minimize communication overhead and so on. So one thing that you can do is data parallelism, where you just split your mini batch across different devices and run each one forward and backward, and then either sum the gradients to do synchronous distributed training, or just make asynchronous updates to your parameters and do asynchronous training. So you can, the white paper claims that you can do both of these things in TensorFlow, but I didn't try it out. You can also actually do model parallelism in TensorFlow as well, but lets you split up the same model and compute different parts of the same model on different devices. So here's an example. So one place where that might be useful is a multi-layer recurrent network. There, it might actually be a good idea to run different layers of the network on different GPUs, because those things can actually take a lot of memory. So that's the type of thing that you can actually do. Theoretically, you can do that in TensorFlow without too much pain. TensorFlow is also the only of the frameworks that can run in distributed mode, not just distribute across one machine and multiple GPUs, but actually distribute training the model across many machines. So the caveat here is that that part is not open source yet. As of today, the open source release of TensorFlow can only do single machine multi-GPU training. But hopefully soon that part will be released too, because that'd be really cool. Right, so here the idea is we can just, and TensorFlow is aware of communication costs both between GPU and CPU, but also between different machines on the network. So then it can try to smartly distribute the computational graph across different machines and then across different GPUs within those machines to compute everything as efficiently as possible. So I think that's really cool, and that's something that the other frameworks just can't do right now. One pain point with TensorFlow is pre-trained models. So I did a thorough Google search, and the only thing I could come up with was an inception module, a pre-trained inception model, but it's only accessible through this Android demo. So that's something I would have expected to be more clear from the documentation, but that's at least you have that one pre-trained model. Other than that, I'm not really aware of other pre-trained models in TensorFlow, but maybe they're out there and I just don't know about them. Bharath says no, so I Googled correctly. So the TensorFlow pros and cons from, again, my quick one-day experiment. It's really good because it's Python and NumPy. That's really cool. Similar to Theano, it has this idea of computational graphs, which I think is super powerful, and actually takes this idea of computational graphs even farther than Theano, really. And things like checkpointing and distributing across devices, these all end up as just nodes inside the computational graph for TensorFlow. So that's really cool. It's also claims to have much faster compile times than Theano. I've heard horror stories about neural Turing machines taking half an hour to compile. Maybe that should be faster in TensorFlow, so I've heard. TensorBoard looks awesome. That looks amazing. I want to use that everywhere. It has really cool data and model parallelism, I think much more advanced than the other frameworks. Although the distributed stuff is still secret sauce at Google, but hopefully that'll come out to the rest of us eventually. But I guess as Bharath was saying, it's maybe the scariest code base to actually dig into and understand what's working under the hood. So at least my fear about TensorFlow is that if you want to do some kind of crazy, weird imperative code, and you cannot easily work it into their computational graph abstraction, that seems like you could be in a lot of trouble. Where maybe in Torch, you can just write whatever imperative code you want inside the forward and backward passes of your own custom layers. But that seems like the biggest worrying point for me about working with TensorFlow in practice. Another kind of awkward thing is this lack of pre-trained models. So that's kind of gross.
So one more comment. TensorFlow is a royal pain in the ass to build. If you're not on a very recent version, if you don't have 0.217, it's basically impossible to build TensorFlow. Most Stanford GPU clusters don't have this, so you can't actually run TensorFlow on basically any Stanford system right now. You can do AWS instance.
Oh yeah, so actually a point about that, even installing on Ubuntu on my own machine that I had sudo to was a little bit painful. They claimed to have a Python wheel that you can just download and install with pip, but it broke, and I had to change the file name manually to get it to install. And then they had a broken dependency that I had to update manually and like download some random zip file and unpack it and copy some random files around. But it eventually worked. But installation was tough, even on my own machine that I have sudo to on Ubuntu. So they should get their act together on that. So I put together this quick overview table that kind of covers what I think people would care about on major points between the frameworks. Like what are the languages, what kind of pre-trained models are available. Question? The question is which of these support Windows? And I'm sorry, but I don't know. I think you're on your own. You can use AWS from Windows. OK. OK, so I put together this quick comparison chart between the frameworks that I think covers some of the major bullet points that people care about. Talking about what language it is, whether they have pre-trained models, what kind of parallelism you have, and how readable is the source code, and whether they're good at RNNs. So I had a couple use cases in, let's see, we've got, holy crap, we got through like 150 slides and we still have 2 minutes left. So let's play a little game. Suppose that all you wanted to do was extract AlexNet or VGG features. Which framework would you pick? Yeah, me too, Caffe. Let's say all we wanted to do was fine-tune AlexNet on some new data. Yeah, probably Caffe. Let's say we wanted to do image captioning with fine-tuning. OK, I heard a good distribution. So this is my thought process. I'm not saying this is the right answer. But the way I think about this is that for this problem, we need pre-trained models. For pre-trained models, we're looking at Caffe or Torch or Lasagna. We need RNNs. So Caffe is pretty much out. Even though people have implemented this stuff there, it's just kind of painful. So I'd probably use Torch or maybe Lasagna. How about semantic segmentation, where we want to classify every pixel? Right, so here we want to read an input image, and then instead of giving a label to the whole output image, we want to label every pixel independently. OK, that's good. So again, my thought process was that we need a pre-trained model here, most likely. And here that we're talking about kind of a weird use case, where we might need to define some of our own logic. So if this layer happens to exist in Caffe, that would be a good fit. Otherwise, we'll have to write it ourselves. And writing this thing ourselves seems the least painful in Torch. How about object detection? No idea? Yeah, so Caffe is an idea. So my thought process, again, we were looking at pre-trained models. So we need Caffe, Torch, or Lasagna. We actually could, with detection, you could need a lot of funky imperative code that it might be possible to put in a computational graph, but seems scary to me. So Caffe plus Python is one choice that some of the frameworks we talked about actually went this route. And I've actually done a similar project like this, and I chose Torch, and it worked out good for me. How about if you want to do language modeling? Like you want to do funky RNNs, and you want to play with the recurrence rule? Torch, what are you guys saying? Yeah, I would actually not use Torch for this at all. So here, if we just want to do language modeling and do funky kind of recurrence relationships, then we're not talking about images at all. This is just on text. So we don't need any pre-trained models. And we really want to play with this recurrence relationship and easily work with our current networks. So there, I think that maybe Theano or TensorFlow might be a good choice. How about if you want to implement batch norm? Oh, oops. OK, bug in the slides. Sorry about that. Right. So here, if you don't want to derive the gradient yourself, then you could rely on one of these computational graph things like Theano or TensorFlow. But because of the way that those things work, as you saw in the homework, for batch norm, you can actually simplify the gradient quite a lot. And I'm not sure if these computational graph frameworks would correctly simplify the gradient down to this nice efficient form. Question?
Is there an ugly way of combining an RNN and Theano with a pre-trained model from Torch, other than like dumping the weights to disk and reloading them and all that?
So the question is how easy is it to combine like a Torch model with a Theano model? And I think it seems painful. But at least in Theano, you can use Lasagna to access some pre-trained models. So plugging together a Lasagna model with something else, I think theoretically maybe should be easier. So here, if you have some like really good knowledge about how exactly you want the backward pass to be computed, and you want to implement it yourself to be efficient, then you probably want to use Torch. So you can just implement that backward pass yourself. So my quick recommendations on frameworks are that if you just want to do feature extraction or maybe fine-tuning of existing models, or just train sort of a vanilla, straightforward task, then Caffe is probably the right way to go. It's really easy to use. You don't have to write any code. If you want to work around with pre-trained models, but maybe do weird stuff with pre-trained models and not just fine-tune them, then you might have a better job in Lasagna or Torch, because there it's easier to kind of mess with the structure of pre-trained models. If you really want to write your own layers for whatever reason, and you don't think it can easily fit into these computational graphs, then probably you should use Torch. If you really want to use RNNs and maybe other types of fancy things that depend on the computational graph, then maybe Theano or TensorFlow. Also, if you have a gigantic model and you need to distribute across an entire cluster, and you have access to Google's internal code base, then you should use TensorFlow. Although hopefully, like I said, that part will be released for the rest of us soon. So that's also if you want to use TensorBoard, then you've got to use TensorFlow. So that's pretty much my overview, my quick whirlwind tour of all the frameworks. So any last minute questions? Question?
How do you compare the speed of these frameworks?
So the question is about speed. So there's actually a really nice page that compares speed, benchmark speed of all the different frameworks. And right now, the one that wins is none of these. The one that wins is this thing called Neon from Nirvana Systems. So these guys have actually written, these guys are crazy. They actually wrote their own custom assembler for NVIDIA hardware. They were not happy with like NVIDIA's CUDA toolchain, so they reverse engineered the hardware and wrote their own assembler, and then implemented all these kernels in assembly themselves. So these guys are crazy, and their stuff is really fast. So their stuff is actually the fastest right now, but I've never really used their framework myself, and I think it's a little less common than these. Although for the ones that are using cuDNN, the speed is roughly the same. Right now, I think TensorFlow is quite a bit slower than the others, for some silly reasons that I think will be cleaned up in subsequent releases. But at least fundamentally, there's no reason TensorFlow should be slower than the others.
I'm just curious about a show of hands, by the way. How many of you people are thinking of using different libraries? So how many of you are thinking of going with Caffe right now? Okay, or Torch? Okay, what else was there? I guess Theano-based carousel lasagna? Okay, or TensorFlow? All right.
All right.
Or how about assignment code?
That's actually not crazy. There were quite a few teams last year that actually used assignment code for projects, and it was fine.
So it's interesting, we have like a very broad distribution.
Yeah, I should also mention that there are other frameworks that I just think these four are the most common. Question?
How about like graphing and visualizing things? Like with NumPy, we have.
Oh, so the question is about graphing and Torch. So Torch actually has an IPython kernel, so you can actually use iTorch notebooks. That's kind of cool. And you can actually do some simple graphing in iTorch notebooks. But in practice, what I usually do is dump my data, run my Torch model, dump the data either to JSON or HDF5, and then visualize it in Python, which is a little bit painful, but it gets the job done. Question?
Does TensorBoard give us the ability to dump our raw data so we can later plot it later?
The question is whether TensorBoard lets you dump the raw data so you can plot it yourself. They're actually dumping all this stuff into some log files in a temp directory. I'm not sure how easy those are to parse, but you could try. It could be easy or not. I'm not sure. Question?
So other than TensorBoard, are there any third-party visualization tools out there that you guys think are useful for, say, monitoring your network access training and things like that?
The question is whether there are other third-party tools similar to TensorBoard for monitoring your networks. There might be some out there, but I've never really used them. I've just written my own in the past. Any other questions? All right, I think that's it.